Hello everyone, my name is Bhaskaran, and in this video we are going to discuss cascodes and how they can help us improve the output resistance. So we know that for, let's say, this one transistor, if you're looking into the drain, then our out would be something like 1 over GDS. But we have certain situations or certain circuits where we can really benefit a lot from having a higher output resistance. Two things come to mind. First one could be current mirrors, right? And so if you haven't, learned about current mirrors, or once you learn about current mirrors, you will find out that one of the properties that we are looking for in current mirrors is high R out. Ideally, um, we would have an infinite route, but we can't obviously have that. So our goal is to increase output resistance as much as possible. And as it turns out, cascoding will help us to increase the output resistance. Another case might be op amps. So, op amps, we need high gain stages, and the gain is usually GM times R out. So if we can improve the R out, then that means higher gain. And so you'll find out that, once we discuss op amps, there's, telescopic and fully cascode topologies where we actually use cascode to improve the output resistance, and, that will give us a higher gain stage in an op amp. So yeah, those are some of the, motivation that's a little bit of a motivation for why we could use cascodes and how we could do better by improving the output resistance. Okay, so let's look at how cascodes actually help us improve the output resistance. We'll start off with an example. So, here, if we had a ground and I asked you the resistance here, you would say 1 over GDS, or to be more precise, 1 over GDS 1. Right? But let's say we're going to make a little modification here in this example. Instead of connecting the source to ground, we are going to add a source degeneration resistor, RS. And now our goal is to find out the new R out. Okay, the R out with this source degeneration resistor. And so I have this small signal model drawn already. And I think if you're, if you just learned how to, find out the small signal resistance looking into a node from my previous video, I think this would be a great exercise to, pause the video here and try to figure out an expression for R out yourself. But anyway, I have done the derivation myself as well, and I can share the work here just so that even if you are doing your own derivation, you can cross-check with the work here. So first things first, looking at the circuit, we can do a KCL at let's say node let's call this node Vx, okay? And so KCL at node Vx. And so this would give us the equation over here after a little bit of rewriting. And then we can do another KCL because this circuit has two critical nodes, and the second node would be KCL, doing KCL at Vs. And that's going to be the second equation for the circuit, and you're going to find something like this. And now we have two equations, and we can, basically substitute this one into the previous equation that we got, and we will end up with a form with an equation of this form. And we can do, again, do a little bit of rewriting and some algebraic manipulation, and you'll find out that V naught over I naught is something like this, and which is basically the same as R out, right? And then again, some simplifying steps, and you would come up with a final expression which looks something like this. So that's the output resistance, including if we include the source degeneration resistor over here. Now let's look at this. Let's look at this expression. All right. So we said a simple transistor looking to drain, the resistance will be 1 over GDS. And with the source degeneration resistor, the R out would be 1 over GDS plus RS times 1 plus GM over GDS. So if you've learned about transistor FOMs, you would immediately realize that this is actually the intrinsic gain of the MOSFET. So by adding the source degeneration resistor, we get this extra term here, which is an increase in R out due to this degeneration resistor. Okay, so that's great. We have found out a way where we can add this transistor at we can add this resistor at the source of the transistor, and somehow the output resistance now is increased, right? And so that's great. Now let's look at cascodes. All right. And the angle that I want you to think about is essentially like we just discussed this circuit and how we can add the source resistor, but source degeneration resistors, like resistors in general on chip, are expensive and they're large, right? And they'll have some sort of variation. So can we do something better? Can we replace this source degeneration resistor by a transistor? Because transistors in CMOS process, MOSFETs are, they're cheap and they're easy to, it's much easier to have a MOSFET in a CMOS process as compared to like a resistor where it would take up more area and there would be a variation and all that sort of stuff. But adding a MOSFET it's pretty easy, right? So let's try to think of this circuit and replace the source degeneration resistor with a transistor. So that would be the transistor here, okay? And this transistor on the top is called the Cascode transistor. Okay, so what we will find out is, looking into this node, the resistance is 1 over GDS. But looking into the node here, if we add this Cascode transistor M2, the resistance looking into the node, into the drain of M2 would be something higher than 1 over GDS, I should say 1 over GDS1. So it would be something higher than 1 over GDS1 because of this Cascode transistor M2. And we can come up, and so one way would be to, you can, if you want an exercise, you can basically draw the small signal model of this circuit over here and find out the R out looking into this node. I have a little bit of a shortcut, just a little quick trick to find out the output resistance if it's Cascode topology. So I'm going to share that with you. So the R out would have three important terms. The first one would be whatever node, whatever terminal you're looking at when you look into the node. So in this case, when you're looking at R out, the first transistor you see looking into the node is M2, and it's the drain of M2. So the first term would be 1 over GDS2, okay? And then plus, then there's a second term, and the second term would be either the intrinsic gain or the inverse of the intrinsic gain, depending on whatever is in the denominator of the first one. So in this case, 1 over GDS, so in the denominator, we have 1 over GDS2. So the second term would be GM2 over GDS2. The point is that this denominator and this denominator should match, okay? So you can decide whether it's going to be the second term is going to be the intrinsic gain or the inverse of the intrinsic gain, whatever is needed to make those two denominators match. So as an example, if the first term was GM2 instead of 1 over GDS2, then the second term should have been something like GDS2 over GM2. Okay, so because like we have to make sure that these two denominators match. Okay, so that's just as an example. All right, so that's the second term. And the third term in this output resistance expression would be the resistance looking into the second transistor. So over here. So that's something we know. That's 1 over GDS1. And that's our third term, 1 over GDS1. So that's the little trick that I have to find out the output resistance of a Cascode topology. So you can even simplify it further and say, ignoring this term, then you can rewrite this as GM2 times RO1, RO2. And you can go even further and say GM2 RO squared. All right, assuming that RO1 and RO2 are equal, right? So that's just how you do, how you can do a quick calculation or come up with a quick expression for the resistance looking into a Cascode topology. All right. And so to further reinforce this concept, I have 2 or 3 more examples of Cascode. So let's go through them one by one so that we become more familiar with coming up with the expression for our out for different Cascode topologies. So let's see example 1. So now it's like we're looking into the source of M2 and the Cascode transistor, which is the M1, is also the source. So let's come up with the output resistance expression. So here, the first, looking into the node, we see the source of M1. So it's going to be GM1 plus, and then the second term is going to be GDS1 over GM1. So that's because we have to match the denominators here, right? And then the third term is going to be whatever resistance we, oh, sorry, don't know what happened there. The third term would be the resistance looking into the second device. So this would be 1 over, since we are looking into the source of M2, this would be 1 over GM2, okay? And yeah, so that's that. And then let's move on to example 2. Again, R out looking into this node. We can say that R out is going to be 1 over GM1 because we're looking into source. And again, GDS1 over GM1 times, and then for M2, we're looking into the drain. So we could say GM2, GDS2. Okay. So that's example 2. Then example 3, again, looking into this node, finding the output resistance. We're looking into the source of M1, so 1 over GM1 plus GDS1 over GM1 times looking into the drain. We are, looking into the drain, it would be 1 over GDS2. And okay, and so example 4, now we have it's still a Cascode topology, but now we have 2 Cascode transistors. So this is going to be interesting. So let's look at this, right? We know that looking into M3 here, this would be 1 over GDS2. Sorry, my bad, GDS3. And looking into the node here, we would have using our little trick there, 1 over GDS2 plus GM2 over GDS2 times 1 over GDS3. And we can approximate this as, if we ignore this term, then it's going to be something like GM2 over GDS2 into 1 over GDS3. Okay. And so let's look at the final R out. The final R out, looking into the source of M1, we have 1 over GM1 plus, and then the second term, which is GDS1 over GM1, again matching the matching the denominators, and then the third term would be whatever we have in pink over here. All right, so that's going to be GM2 over GDS2, 1 over GDS3. So that's our final expression for this kind of Cascode. All right, so that's example 4. And so, okay, let's talk about cascoding. And so far, we have, we've talked about, um, how we can add this cascode transistor M2, and all of a sudden, we are getting a higher output resistance, um, which is higher than 1 over GDS2. Uh, and and so, yeah, we have basically increased our output resistance by adding this cascode transistor. But what are the downsides of cascoding? So let's look at that. Is cascoding a free lunch? Definitely not. And so let's look at the price we pay for cascoding. Now, I want you to look at three cases. Let's say we start off with one transistor and we get the output resistance 1 over GDS1, right? And I tell you to do better to improve the output resistance, and you say, no problem. I can add one cascode transistor and now my output resistance is higher. And I'm like, okay, that's not enough either. And you're like, okay, no problem. I can add a third transistor, right? And now the output resistance is even higher. So if these expressions, we can also write these expressions as, so this is 1 over GDS, sorry. This is 1 over GDS1, or we can write it as RO1, right? This we can write it as, in a more simplistic way, we can write it as GM RO squared. And here we can write it as GM squared RO cubed. So look at this, like GM squared RO cubed as compared to just RO, right? Just RO in the first case. So we have made great gains in terms of the output resistance, but what's the price that we are paying? So first thing that we see is we have to supply all these bias voltages, VG1, VG2, VG3. These voltages have to come from somewhere, right? And you have to generate them. And so the more cascode transistors you keep adding, the more bias voltages you have to provide to keep these transistors into saturation, right? So that's one thing. But then also look at, to keep these transistors into saturation, you have to ensure that the overdrive voltage is enough, right? And so here, if we have one transistor, it would be just VOD to keep M1 in saturation. But if we have M1 and M2, M2 being the cascode transistor, now we have VOD2 plus VOD1, right? And so going further, if we add three transistors, so if we have two transistors, M2 and M3, which are cascodes, then we have VOD3 plus VOD2 plus VOD1. So we have to have like all these overdrive voltages at a very minimum at this node. At this node, we have to have all like minimum VOD plus VOD1 plus VOD2 plus VOD3 to keep all of these transistors into saturation, right? So in other words, imagine if we have a supply of 1 volt, okay? And let's say, for an example's sake, VOD of these transistors is 200 millivolts, okay? So then that means the output swing, the output available swing is from 1 volt, from 1 volt, from 1 volt to 200 millivolts, okay? So that's in total, that's a delta of 800 millivolts of swing that you can get, and your output can swing between like the peak to peak 800 millivolts. So that's that. And then let's say we add a cascode transistor, M2, in the second case. Now this is 400 millivolts, right? The minimum is now 400 millivolts, and the supply is still like one volt. So now the swing can only, your output can only swing for 600 millivolts, right? So we went from an available swing of 800 millivolts. In the second case, our swing is reduced to 600 millivolts. Let's look at the third case, right? Now the minimum needs to be 600 millivolts because we have 200 millivolts from the first M1, from 200 millivolts from M2, 200 millivolts from M3. And so that's 600 millivolts in total. And again, the high side is still, the high limit is still 1 volt. And so now our available swing would be a delta of 400 millivolts. right? And so on and on. And so you can imagine like your basically your available output swing is decreasing as you add these Cascode transistors. And on top of that, you have to ensure that you're providing these bias voltages, VG1, VG2, VG3, whatever, to keep these transistors in saturation and bias them properly, right? So that's one of the major things with Cascode is that you have the more transistors you have in Cascode, the lower voltage headroom you have, or or lower output swing. Okay, so that's the downside of Cascodes, and again, this trade-off between headroom and higher output resistance will keep coming over and over again when we discuss Cascode current mirrors. It will come again when we see op amps that use Cascode topology. We'll be pretty much discussing the same thing, that we've gotten a higher gain because our R out is high, but then the swing of the op amp would reduce because we are using this Cascode topology. So this trade-off is important, and it will pop up again in later videos as well. So that is pretty much Cascodes. Again, as a summary, we discussed at first we discussed why we need higher output resistance. We talked about current mirrors that might need that can benefit from higher output resistance. We talked about op amps and how we can increase the gain by increasing the output resistance. And then we looked at a simple example where we increase the output resistance by using a source degeneration resistor. And then we tried to get the same effect, but replacing the source degeneration resistor with a transistor. And so that's basically the Cascode topology here. And yeah, basically we discussed a shortcut for finding the output resistance for a Cascode topology. And then we did 4 examples finding the output resistance in different Cascode topologies. And finally, we discussed a downside of Cascode, which is a lower output swing. And again, the need for these additional biases to keep the transistors in saturation. So that's pretty much it for this video, and I hope to see you in the next one. Cheers.